Okay, so while you're kind of starting that, okay, a couple of quick reminders here about work energy theorem. Right? First off, steps. Write down our givens. Okay? Read the context of the question carefully, because in the context of the question we need to figure out which type of energy is being changed. Right? Once we've figured out which kind of energy is being changed, then we can set up the work energy theorem. Work is a change in whatever type is changing. We can set up force times distance is equal to initial or final energy minus initial energy, whichever type it is, if it's necessary to use force times distance. Sometimes they outright give us the work. Okay? And then manipulate and solve. All right? Those are the steps that we went over yesterday. Okay? How many people have done this one already? How many people are lost? Pitcher throws a ball, all right, and its mass is 0.250 kilograms. So that's our first given. Mass equals 0.250. All right. He exerts 300 newtons of force, so that's F, over a 2.2 meter path. What does meters measure? Distance. All right. I got force and distance here, so what's going on in this question? Work, which means energy is changing. Since the question asks us for the speed of the ball, what kind of energy is being changed? Kinetic. All right. So I know that my work is going to be changing the kinetic energy of the ball. Now, it doesn't outright say this, but if you've ever watched baseball, okay, the pitcher stands on the mound and holds the ball in his glove and looks at the catcher to get the signal. What's the kinetic energy of the ball at that point? Zero, because it's not moving. So we can assume then that the initial kinetic energy of the ball is zero. That's what we have to assume. Okay? So we know then that we've got force times distance equals 1/2 mvf squared, our final kinetic energy, minus 1/2 mvi squared. Now, we can simplify because we just finished saying the initial velocity of or initial speed of the ball is 0, which means the initial kinetic energy of the ball is also 0. So we can just get rid of that. It's 0. Subtracting 0 doesn't mean anything. So I'm trying to find the speed at which he will release the ball. So what part of this equation am I looking for? I'm looking for VF, right? Okay. So how do I get VF by itself? How do I get VF by itself? Divide. Divide 1/2 m, okay? And that leaves me with VF squared. Square root, right? Okay, so now I can plug in my numbers and find out what my final speed is going to be. All right, so VF is going to equal the square root of 300 newtons, the force he exerted on the ball, multiplied by the distance over which he exerted it, divided by half of the ball's mass. And then all of that square rooted. Okay, so we'll have 300 times 2.2, okay, divided by half of 250, which is 0.125. All right, gives us 5,280. Then I got to square root that. All right, ball leaves the pitcher's hand at 72.7 meters per second. Okay, that is definitely a fast ball. That thing hits you, it'd leave a 3-foot hole coming up. Okay, yeah. Okay. No pitcher's going to throw a ball that fast. Okay, that is ridiculously fast. Okay, does that make sense? Right, that's a lot like some of the ones we were doing yesterday. Anyone need that one anymore? Okay. This is very much like the example I did for you with the playground zone speed limit. Right? So I want you guys to give this one a try. This time we're solving for distance. Okay? Give it a try. Okay, so on this one, Okay, the car applies its brakes with a force of 10,000 newtons, so we know what F is. Okay, it's 10,000 newtons. All right. It slows down from 20 meters per second, so that's our initial speed, to 6 meters per second. Okay. If the car has a mass of 1,700 kilograms, how far did it travel? All right, so we're looking for D here. All right, what kind of energy is being changed in this question if it's slowing down? Kinetic, right. So our work equals the change in kinetic energy. Force times distance, since they give me force and ask for distance, I've got to plug that in, equals 1/2 mvf squared minus 1/2 mvi squared. And I'll have to do both of those, but that's okay. All right. I need to get distance by itself, so what do I do with force? Divide it over to the other side. Okay, so now I can plug in my numbers. Distance is going to equal 1/2 times 1,700 times 6 squared minus 1/2 times 1,700 times 20 squared divided by the force, which was 10,000 newtons. Now, your number, when you do this, comes out negative. But since it asked for how far, would you actually include that? Because how far is distance? The only reason this comes out negative is because the car is losing energy. And the equation is set up to show that that means that's negative work. All right? The car is transferring energy away. It doesn't mean it went backwards. All right? It just means that it did negative work and it lost energy to the surroundings. That would be fine. That's how you would get it to come out positive. And in fact, the force should be negative because the force is backwards. Okay? All right. So when we do this, okay, we've got, we should make this, like we said, a negative force, as it is directed backwards, and force is a vector quantity. Okay. We'll have 0.5 times 1,700 times 36, okay, minus 0.5 times 1,700 times 400, that's 20 squared. Okay, and then we're going to divide that by 10,000, by negative 10,000. Okay, and we get 30.9 meters. All right. Everybody okay with that one? Okay, and guys, honestly, I had one just like that on the unit exam not long ago. Okay, it's pretty common to have them like that. Okay, so you've had two that were about kinetic energy. Try this one. All right, let's give this one a try then. So I've got a slingshot aimed straight upwards, drawn back 0.4 meters. So there's my distance, 0.4 meters. Okay, with a force of 1,500 newtons. Okay, so we got force and distance. We know there's work going on. Okay, and work is going to mean that there's a change in energy. Since it's asking me about height, what kind of energy is being changed? Potential energy. Okay, so it tells us it reaches a maximum height of 30 meters. So where should we assume the initial height most likely was? 0. It doesn't say that, but you're usually standing on the ground when you fire a slingshot. Okay, so we're going to assume that that's where you were. Okay, that you were on the ground. All right, so I've got distance, force, and height, and I'm looking for mass. So work's a change in potential energy. So force times distance is going to equal m times g times h final minus m times g times h initial, my gravitational potential energy formulas. We just said initial height was 0. So what is m times g times 0? 0. All right, so I'm just going to get rid of this. I don't need it. It's 0. And I'm going to manipulate to find the mass of the rock. So how do I get mass by itself? Divide by GHF. All right, so we're going to have 1,500, okay, multiplied by 0.4 divided by 9.81 times 30. Okay, now, they don't outright give us the 9.81. Why not? You already know it. Yeah, anytime you're dealing with potential energy, you have to use 9.81. It's on your formula sheet. Okay, it's a number you use all the time. So we'll have here 1500 times 0.4, okay, divided by 9.81 times 30. Okay, it's 2.0 kilograms. Okay, is that one making sense? Okay, that would be a lot like what I might ask on a unit exam. And again, it's not a difficult mathematical question. Okay, it's just a matter of can you interpret the context of the question to know what kind of energy is changing. That's the biggest stumbling block. All right. Okay. All right, last one. Try this one here. Okay, let's have a look at this one. So they tell us, first off, the amount of work being done. So we know we're not going to have to put in force times distance because they already told us, okay, what that equaled, 4,000 joules. Okay, the mass of the box is 25 kilograms, and the final height of the box is the initial height of the box. The initial height of the box is 7 meters, and we're looking for the final height of the box. Okay, so what kind of energy is changing in this one? Potential. It's all about height. Okay, so there we go. So work is going to equal m times g times hf minus m times g times hi. I need to get hf by itself. So I should move what's not attached to it first. What's not attached to it? mghi. So I'm going to add that to both sides. So I'm going to have work plus mghi equals mghf. How do I get hf by itself? Divide by mg, right? Does mg cancel over here? No. Okay, so now we can plug in our numbers. All right, we're going to have that the final height is going to be 4,000 joules plus 25 times 9.81 times 7 divided by 25 times 9.81. Okay, so when we plug in our numbers here, okay, we're going to have 4,000 minus 25 times 9.81 times 7, okay, and then divided by 9.81 times, sorry, that's not right, 9.81 times 25. Alright, so we get yeah, 9.3 meters. Is that what you guys are getting? I was looking at my math here. Yeah, 25 times 9.81 times 7, then divided by, yeah. Okay, everybody with me there? Tilly. They gave it to me in the question. Because I'm subtracting mghi over here. So to move it, I have to do the opposite, right? Right, so I got to bring it over here. Yeah. Okay. Any other questions on that one? 9.3 meters was the final height. Okay. On Monday, we're going to probably do a lab with rubber bands and spring scales and stuff on work and energy. And then next week, we'll spend a couple more days on work energy theorem. Sorry, Tuesday, we'll do that. And then we'll do some more work energy theorem stuff before moving on to law of conservation of energy. All right. Have a good long weekend, guys. Check on Monday night. It's possible. Yeah, guys, there could be a quiz on Tuesday. Check Monday night. Check Google Classroom Monday night.